So we've been working with graphing rational functions and finding all different types of asymptotes and describing behavior around those. So this is an opportunity to solve or review solving rational equations and inequalities. So let's take a look here. We know that from the beginning, when you started working with rational equations a few years ago, you were taught to multiply by the LCD, which is exactly what we are going to do here. So we're going to multiply in example 1a by the LCD, and that would be x, okay? But of course, anytime we multiply by an LCD, we have to be aware we may pick up extraneous functions or extraneous solutions. So if I multiply by x, I end up getting a quadratic. Put everything in decreasing order. Fortunately, this does factor, and I get x to be 5 and x to be 2. And check for extraneous. The only issue we would have here is we got x to be 0, which we did not. All right, let's take a look at example 1b. So another rational equation. So we're going to multiply both sides by the LCD, which would be x times x minus 3. And so when I multiply every term by x times x minus 3, I end up with x minus 3 minus 2x equals 4x times x minus 3. So once I distribute and put all my like terms together, I do get a quadratic, but in this case, I end up having to use the quadratic formula. So at any time, just as a reminder, if you want to stop the video, work out the problem, and then watch to verify your answer, please feel free to do that. Okay, so we know that we would have an issue, so to speak, if we had x to be 0 or x to be 3, and we did not get that, so we are good with that. All right, so now let's take a look at example 2. We have another rational equation, but we have these three denominators, but fortunately, hopefully you recognize that x plus 5 times x minus 2 is x squared plus 3x minus 10, so that will be our LCD that will multiply all terms by. So that leaves me with 3x times x minus 2 plus 1 times x plus 5 equals 7. So when I distribute and put all like terms together, I end up with another quadratic. And this one did factor, and I end up with negative 1/3 and 2. However, if you take a look at 2, this would be undefined, so x equals 2 is extraneous, so our solution is negative 1/3. Okay. So let's take a look at the 2b here. To be or not to be. All right. So again, if you have a hard time telling what the LCD is, you want to make sure and factor your denominators. So that is something that I didn't mention, but if it's not factor, sometimes factoring it helps you see what is all involved. So we know that we have a factor. This would be x times x plus 2. So the LCD would be x times x plus 2. This is an x, this is an x plus 2. So I'm going to multiply every term by x times x plus 2. So if I take 3, my x plus 2 is reduced, gives me 3x plus 6, because x times x plus 2 reduces with x squared plus 2x, and I end up with 3 minus x times x plus 2 because x reduces. So we end up with more quadratics, so I distribute and bring like terms together, and I end up solving this by taking out a GCF, and I get 0 and negative 2. However, again, anytime we multiply by an LCD, we have the chance to pick up extraneous, and both of these are extraneous, so this would actually be no solution. So hopefully you found that pretty quick and easy, because when we have equations, we can do anything we want as long as what we do to one term we do to the other, multiply by the LCD. All right, now solving rational inequalities. Inequalities is a whole different situation. It is just like when we solve the absolute value inequalities, the combination of radicals with inequalities, we used our graphs. So reading our graphs will be very important to working with these. All right, so why can't we, if we have a rational inequality, just multiply by the LCD like we did with equations? Well, here's the problem, for example, that if we had an inequality and we multiplied all sides by x, do you know if x is positive or x is negative? We don't, so therefore we don't know if the inequality sign should reverse. So this is why we should look at these graphically. So I'm going to explain the approach that I use, and it's a combination of graphing and algebra. All right, so first of all, let's take a look at the first example. Actually, I'm going to explain my approach here. All right, we are going to always have our inequality set less than or greater than 0. Why do that? Well, because it is easy then when we graph it to read where is this graph below 0 or where is it above 0. Now, let's also think about then why I want to find my intercepts. So my directions are, my approach is we're going to use graphing, but we're going to find our asymptotes and our intercepts. Well, for one, we're going to find our intercepts because isn't that the place where the graph is above or below the x-axis? Now, why am I asking you to find your asymptotes? Asymptotes, because isn't that where a graph can change direction? All right, so let's take a look at 3a. All right, so taking a look at 3a, we definitely don't have a rational function, or we need to put it in rational function form. So the good news is this is greater than 0 already. So I'm going to get a common denominator of x minus 3 over x minus 3. So now I'm going to add my terms with the common denominator, and now here is the inequality that I am working with. I've not changed anything. I just got a common denominator and made it a rational function. Now, how am I going to use my graph? Well, I am asking what values of x make this graph above the x-axis? Where is it above 0? Okay, so before I go to my calculator, because as you know by now, the rational functions, sometimes reading the calculators can be a little misleading. We have to make sure and put our pieces together. All right, so I know that in this function I have x equals 3 is my asymptote. Now, my x-intercept would be 11/4. Let me go back here, because I know that if I put 0 in for y, my x-intercept, anytime that's going to be, I set my numerator equal to 0. Everybody understand that? Hopefully. That goes back to where we find intercepts when we were graphing. Okay, so my x-intercept is 11/4 0. So now, what I encourage you to do, just like we did with graphing functions, I encourage you to graph your x-intercept and to graph your asymptote and then put it on your calculator. Okay, so now let's read your calculator. So we're asking what values of x, where is this function above the x-axis? All right, well, here's my x-intercept, so isn't that anything below 11/4? Here's my asymptote, isn't that everything greater than 3? Now, in algebra, you might have been taught to check in intervals. And again, what intervals? Well, I would use my asymptote. It goes back to the connection between the algebra and the graphing. I would use my asymptote and my x-intercept. All right, I would put them in how they would appear on the number line. So I would check anything below 11/4. So if I put in a 2 to this, I end up getting a true statement. So if I put in a 2, I get -3 over -1. That's positive. That's a true statement. Now, 11/4 and 3, they're really close together. If I put in a 2.8, I'm going to get a false statement. Excuse me. And then if I put in 4, I end up with 5, which is greater than 0, which is a true statement. So you can do this two ways. Once you find your intercepts and your asymptote, you can set up and test intervals, or you can just use that to read your graph. Okay, let's take a look at 3b. All right, thankfully, this is already less than 0, and we already have a rational function. So we are looking what values of x, where is this function below 0, where is this function below the x-axis? All right, so I could just graph it and try to read the graph, and that's fine. But we also, though, helping us interpret the graph, let's find our asymptotes. All right, so I'm going to factor my denominator, and my vertical asymptotes are at 2 and -2, and I have an x-intercept at 1, 0. So again, I could read, if I were you, I would graph my asymptotes, graph my intercept, and then I would go through and read or put my graph in my calculator and then read where is this below the x-axis. And notice there's always a change in direction or something that happens at the asymptote or the intercept. That's why we find them. Okay, so we're asking where is this less than 0? Where is this below the x-axis? Well, it looks like everything less than -2. It looks like everything between 1 and 2, and then that's it. All right, so my answers are everything less than -2 and everything between 1 and 2. Now, could I have done the algebra? Once I figured out my asymptotes and my intercept, could I have set up intervals if I wanted? Sure. If I put in -3, I end up with a negative value. That is true. If I put in 0, I end up with a positive. That's no. it's not less than 0. If I put in a half, I end up with a true statement. If I put in 3, I end up with a false statement. Okay, I'm going to skip 3C and I'm going to go to 3D. So I'd like you to try 3C on your own, and let's go to 3D. Okay, so now I know that some people are going to think, all right, I'm just going to go ahead and do this as it is and use the line y equals 3. That is okay, but then you have lost the point of the easily reading the graph of where is this graph below the x-axis. So I would encourage you in every problem, I would get everything to one side less than or greater than 0. So I'm going to subtract 3. I'm going to get a common denominator. I'm going to distribute and put my like terms together. So at this point, if you want to stop the video, get everything on one side, which is nothing new. We've been doing that for so many things to find solutions. All right. Get a common denominator, put your like terms together. Okay, so same approach. I could go ahead and throw this on my calculator, but what I'm going to do first is I'm going to find my asymptotes and I'm going to find my x-intercepts. All right, because I'm going to be reading where is this graph below the x-axis? Where is it less than 0? So my asymptote will be at x equals -2, and my x-intercepts, if I factor this, my x-intercepts are 5, 0, and -1, 0. So before I put this on my calculator, I graphed my vertical asymptote and my x-intercepts. Now I will tell you that when I went to graph this, I only got this part of the graph. All right. However, if I have a vertical asymptote in a rational function, we should know by now that this divided our graph in half. Okay. So I should have suspected that something was here, and you can always check your table on that as well. So I adjusted my x and y mins to -20 and -20, and I did see this part. Okay. So again, where is my graph below 0? Well, I can see everything less than -2. And I can see everything between -1 and 5. Now, could I have set up and checked points between -infinity and -2? Yes, I could have put in -3 and I would have got a true statement. I could have checked numbers between -2 and -1, -1.5, I would have got a false statement. I could have checked numbers between -1 and 5, like 0. Very easy to see. I'm going to get a true statement. -5/2 is less than 0. And I could have put in a number like 6. Anything bigger than 5, and I would get a false statement. Okay, so one more. Let's take a look at example 4. I want you to change example 4, the first problem, to x squared minus 1 over x squared plus 1 is less than or equal to 0. And we're going to do the same approach. Okay, so thankfully we have a rational function, a polynomial over a polynomial, and it's less than or equal to 0. So we don't have to move anything around. So we're going to do our same approach. We're going to find our asymptotes and our intercepts, okay? And again, I want you to understand, why do we find our asymptotes and intercepts? Well, the intercepts, we find the x-intercepts because if we set every inequality less than or greater than 0, those are defining points, all right, where it's above or below. Secondly, why do we find asymptotes? Because asymptotes are where the graph changes direction. All right, so let's see here. Is there anything in my denominator, anything going to make this 0? I mean, if I try setting this equal to 0 to find that, I'm going to have imaginary answers. So there are no vertical asymptotes. So that should be a big, like, flashing light saying, oh, no asymptotes. There's not going to be any breaks in the graph. This is going to be continuous. All right, what would my x-intercepts be? They would be 1, 0, and -1, 0. So no vertical asymptotes to graph. I'm going to graph my x-intercepts, and now I'm going to put this on my calculator. So again, if you want to stop this, put it on your calculator to see. Not a surprise, we do get a continuous function, and now I read my graph. Where is this below or equal to 0? Everything between -1 and 1 and including 1. So, in summary, solving rational equations, we just multiply by the LCD and we have to watch for extraneous solutions. However, when we are working with rational inequalities, it's a whole different situation because we can't just multiply by a variable because we don't know if the sign has changed. So we find our vertical asymptotes because that's where the graph could change direction. We find our intercepts and we set it less than or greater than 0.